Comparative planetology is the name for discussing solar system properties to look for general principles that underlie what's going on, not worrying too much about the particular details of any one planet. Remember, the solar system is our backyard. We know it well, we've sent space missions throughout the solar system, and we've even landed on a couple of these objects and brought back samples from the closest of them, the Moon. In comparative planetology, we look for the common features and then use that to inform how our solar system formed and how we think other solar systems around other stars also formed. The general properties we see are a set of terrestrial planets that are small in mass and size, that have high density in their material, rocks and metals, that are solid in their surfaces because they are not hot enough to form molten liquid or rock, that have few moons, if any, and no ring systems, and that are fairly close to the Sun. Remember, Mars is only 1.5 times the distance of the Earth from the Sun, so the 4 terrestrial planets are all concentrated in that inner zone, whereas the outer planets extend to 40 times the Earth-Sun distance and are distributed over much larger regions in the solar system. The outer planets, or Jovian planets, are quite different. They're much larger in mass and size, and most of their material is hydrogen and helium, which is what the Sun is made of. They're inferred to have rocky cores that are super-Earth in size, perhaps 3 to 5 times the Earth's mass. Each of these giant planets has a ring system, although for 3 of them the rings are quite subtle, not as dramatic as that of Saturn, and they all have moon systems, extending up to dozens for Jupiter and Saturn. The giant planets are far from the Sun and correspondingly cold. However, at the base of their atmospheres, the temperatures may be above room temperature, even extending up to hundreds of degrees centigrade. The dichotomy between the terrestrial planets and the Jovian planets is clear if we look at scale models. The terrestrial planets are all an order of magnitude or more smaller in size and several orders of magnitude smaller in mass than any of the giant planets. In addition to being concentrated in the inner solar system, by Kepler's laws of orbital motion, the terrestrial planets have substantially faster orbits. Mars goes around the Sun in about 2 years. Meanwhile, the outer planets have larger orbits, Jupiter 12 years, extending out to nearly a century in the outer solar system. Seasons on Uranus last 42 years, each for summer and winter. Uranus has no spring and fall because its tilt is 90 degrees. This dichotomy in properties is clear if we look at the details of the mass, size, distance, and density of the planets in the solar system. You can also see that the other objects beyond the planets, such as comets and asteroids, are much smaller than any of the planets and smaller than any of the moons. Comets, we believe, are between 5 and 10 kilometers across, and most asteroids are between tens and hundreds of kilometers, with the largest being about 1,000 kilometers in diameter. The composition of planets in the solar system is determined by the condensation curve, the distance from the Sun at which different materials can be solid or liquid. In the very inner solar system, interior to Venus's orbit, materials like hydrogen, rich compounds of methane, water, and carbon dioxide and carbon monoxide are all in vapor or steam form and are generally driven from the system. In the outer solar system, these materials take a solid form and can be mixed with rock as ices. The terrestrial planets all have rocky mantles surrounding mostly metallic cores, made primarily of iron and nickel. The outer planets have rocky cores of unknown composition because we've never diagnosed the details of the rocky cores. They're invisible from the Earth. Also, the base of the atmosphere of the giant planets is a very strange state of hydrogen. Technically, it's a liquid metallic form of hydrogen under pressures of hundreds of atmospheres and at temperatures of hundreds of degrees Kelvin. It's extremely difficult to create this form of hydrogen on the Earth anywhere. The simplest view of a planet is just a rock in space, heated by the distant Sun. But there are 2 substantial modifications to the temperature you might calculate for the surface of such a rocky planet. The first is due to atmospheric heating of greenhouse gases. The larger a planet, the more able it is to hold an atmosphere. The more massive planets can hold heavy gases like nitrogen, oxygen, and carbon dioxide. Carbon dioxide and methane in particular are greenhouse gases that trap radiation. So the equilibrium temperature of a planet that holds an atmosphere is likely to be hotter than if that planet was just a rocky body in space. Using the energy balance of the Earth as an example, there is an extra 324 watts per square meter that is converted into additional heat at the Earth's surface, raising what would be a temperature of minus 14 degrees Celsius, if the Earth had no atmosphere, to a mean temperature at the Earth's surface of plus 18 degrees Celsius. This is a mild form of greenhouse heating. Venus has an extreme form of greenhouse heating, where the same phenomena has raised the surface temperature by hundreds of degrees. The second modification to a planet from being just a pure rock in space is radioactive heating that occurs naturally within the rocky material. Trace amounts of naturally occurring radioactive elements release heat into rock, and that heat gradually diffuses out through the rocky material to the surface. If a planet has sufficient mass, that heating is sufficient to turn the rock into magma, almost a sluggish liquid. That magma moves by convection currents, and when those convection currents reach the surface, we have volcanism and plate tectonics. This is a substantial modification to the way a planet behaves. We can see it in the difference between, for example, Venus, which is heavily volcanic, and Mercury, which is a geologically dead rock. Tectonic activity even couples to the atmospheric effect just mentioned, because volcanism releases carbon dioxide into an atmosphere, which causes a greenhouse effect, further heating the Earth's surface. The combination of greenhouse effect caused by the planet's mass and volcanism could substantially change the surface of a planet. Comparative planetology is the study of solar system where we look for general properties that we hope might apply in other solar systems. The general dichotomy is between the rocky terrestrial planets and the large gas giants found further out in the solar system. We have a reasonable story as to how this happened. Other modifications in the property of a planet happen from the gases that it can hold by its gravity, which may heat the surface through greenhouse effect, or volcanism. The larger the mass of a planet, the more likely it is to have radioactive heating, which will drive tectonic activity.